Hi, today I'm going to talk to you about boats. If you came here because of the thumbnail, don't worry, we're going to get to the big model in a little bit. But if you're unfamiliar with the channel, one of the things we try to do here is not just use the videos as a way to highlight projects that we've completed, but to go through some of the underlying principles behind the design, as well as explain some of the techniques we've used and admit some of the mistakes that we've made, in order to allow you to either reproduce our results or to use some of the ideas on similar projects that you may be involved in. Now, I've owned, sailed, bought, and built a variety of boats over the years. And I have to say, even though it's kind of fun sitting around on the deck of a luxury yacht drinking a martini, it's generally more fun the smaller the boat is. You know, it's a lot of fun paddling around on a little kayak in a secluded waterway, or hanging your rear end out over the side of a Hobie Cat as, you know, the one hull starting to lift up in the air. And one of the other advantages about small boats is because they are small, they're less expensive, they're easier to transport, to store, they're easier to construct. You don't have a lot of the expense associated with insurance. You don't have a dock space that you have to rent or a mooring. And in addition to that, if you do decide that you want to build a boat, it's just a more approachable project. Now, one of the difficulties, though, with a small boat is it's small, and therefore it usually has a limited capacity. You've got maybe one, maybe two people that you can carry, limited cargo, and they tend to be unstable. You know, there isn't many people, I think, that haven't either fallen out of or nearly fallen out of a canoe. And so what I want to do today is I want to go through the method that we can use to build what's probably considered a moderate-sized boat, but take advantage of a lot of the features of a little boat by constructing a boat that is modular, with a half a dozen to a dozen major components that can be snapped together and snapped apart. We can either bring this to a site that we want to launch it at, or we can store it in individual pieces, which makes it a lot more approachable. Now, in addition, the design of the boat, to maximize the flexibility with a modular design, takes advantage of using a multi-hull versus a mono-hull. And part of the reason is that when you divide the hulls up, you've obviously got lighter components. In addition, a multi-hull not only looks pretty sexy, but it also has a higher stability than a monohull. Now, the reason that the multi-hull is more hydrodynamic, or will move more quickly for the same amount of power, has to do with understanding a little bit about the physics of drag. Now, there are three major areas where drag will occur relative to the movement of a displacement type of hull through the water. In all of these discussions, we're not talking about this sort of skittering activity as a planing boat skitters off across the top, but when a boat is pushing its way or floating through the water. The first source of drag is skin surface drag. Obviously, a smooth surface will travel more easily through the water than a rough surface. And you can finish, whether it's a single hull, a monohull, or a multi-hull, to the same level of smoothness, depending on how much work or money you want to spend. And actually, a monohull will have higher drag for a given amount of speed than a multi-hull, again, simply because of geometry. When you divide the hull into multiple components, you're going to reduce the volume more quickly than you do the area, and so the drag will actually be higher with the multi-hull. An easy way to visualize that is with, say, a canoe. If you were to split a canoe longitudinally and then cover the exposed surfaces with a piece of plywood, if you load the structure, the multi-hull canoe versus the monohull pre-cut canoe, to the same amount of displacement, you're obviously going to have more water in contact with the surface, and the drag will increase. The drag with friction increases as a square of the velocity, but it tends to be only dominant at the extreme low end of the speed scale, couple 3 knots. and it is the dominant form of drag. But once you move above that point to higher speeds, two other components come into play that become more important. One is due to potential energy. When the boat moves through the water, say one hull length to the next hull length in a unit of time, it has to displace an amount of water equal to its weight or its mass. And when that water is displaced, because water doesn't compress, it has to lift that water out of the hole that it is drilling through the water and elevate the water around it. So the sea level or the lake actually has to elevate slightly in an area around the boat. And so therefore you have to invest potential energy to lift that water out of the hole. Now that drag will increase linearly with velocity, and that makes sense simply because if you're moving twice as fast, you have to move two masses of water out of the airway in the same amount of time that you had to move one if you were moving half as quickly. And that drag is going to be the same for the monohull and for the multi-hull. But the real dominant factor has to do with kinetic energy. There is an equation that represents the amount of energy that you have to impart in something when you move it. And that equation is 1/2 mass times the quantity velocity squared, or 1/2 mv squared. When you move the boat through the water, obviously you have to not only lift the water out of the way, but you've got to get it over there. You've got to move it. So you have to impart a velocity to it. And the faster you have to move the water, the more energy you need. Now, when you move a given quantity of water out of the way, the multi-hull will have to move the water less distance simply because it tends to be narrower. And so this velocity, or this energy, goes up very quickly because if you double the speed of the boat, you double the mass. That's the m. If you double the speed of the boat, the water has half as much time for any given shape to get out of the way. And so therefore you double the velocity and you square it. So doubling the speed of a boat through the water increases the amount of drag associated with 1/2 mv squared 8-fold. It cubes it. And so that becomes the dominant factor, and that's the real advantage of the multi-hulls because the hulls are thinner. Now, a couple things about the shape of a hull. Because of the fact that you want that velocity to be as low as possible, that's why you want the front end of a boat to be tapered, unlike Grandpa's pontoon boat with its blunt end. By making it smoothly tapered and slowly tapered, you give the water more time to get out of the way. The velocity is less, and that's important for any kind of a boat. In addition, and a little bit more subtle, is the reason you taper the rear end of the boat is that when that water eventually flows into the void that's left behind the boat when it moves to its new position, that water flowing into that area will actually cause a small amount of force in the direction of motion, just like when you take a slippery pumpkin seed and you squeeze it between your fingers and it pops out laterally. The same thing is happening with the rear end of the boat. You're recovering some of that potential and some of that kinetic energy with the flow into this space. And that is why a swordfish or a tuna fish or a boat tends to be tapered at the rear end. So these things tend to define the shape of a boat. Now, multi-hulls, not only having the advantage of being easily modular or breaking them apart, also have the advantage of being a little easier to construct because there's just a smaller scale with everything that you build. One of the things that I have discovered in building a number of boats by a number of different techniques is that a lot of the work can be spent on jigging and aligning and creating the fixtures that are going to build the boat. And the other one is fabricating some of the precision components. And so the design that I'm going to show you today is going to allow you to produce a boat of extraordinarily high hydrodynamic efficiency, but also incredibly easy to build at the same time. And what we're going to do is we're going to use two techniques. One is called stressed plywood, and the other one is called stitch and glue. And by combining those techniques, we can build a full-size hull like the one that you're going to see a little bit later in the video with a couple of guys with average carpentry skills and average tools in a long weekend. Now, in order to design specifically the shape of the boat, we're going to take advantage of the fact that there are a lot of similarities between airfoils and hydrofoils. And there's a very good website, we'll put the description or put the link in the description below this video, to Airfoil Tools. It provides thousands of different types of airfoils. It gives you calculators and design programs that allow you to produce a variety of different types of airfoils. we're going to use a symmetrical airfoil called an NACA, or National Advisory Committee on Aeronautics, 4-digit airfoil. Now don't get intimidated by all the words in the letters. It's actually very similar. It's a symmetrical airfoil, and so when they specify NACA airfoils, there will be 4 digits that follow them. The first 2 of the 4 digits represent a non-symmetrical airfoil, and so in our case, these digits are going to be 0 and 0, naught and naught. We're not even going to pay attention to them. The last 2 digits in the 4-digit designator are 0 to 100% of width versus length. So if you build an airfoil that's 1/10 as wide as it is long, it'll be an NACA 0010, or 10%. We're going to be building a 0009% symmetrical NACA airfoil and take advantage of the plywood and the stitch and glue technique to build this thing very quickly. Now, I'm going to open this up and kind of show you what's involved. This system is going to take advantage of the fact that when you take monolithic pieces of plywood, in this case we're just using a thin fiberboard because it's inexpensive and easy to work with, but in the case of building the boat, you're going to use sheets of plywood to do this. And we're going to take advantage of the fact that when you take sheets that are very homogeneous and you support them at a couple of points, they will inherently bend to form what's called a fair curve. In boat design, fair means my fair lady, pretty. It also tends to mean no discontinuities and generally very smoothly changing curvatures, which serendipitously tend to be hydrodynamic. The water flows around them very efficiently. And the other part of the technique that we're going to use is called stitch and glue. And what that originally was designed to do is to allow you to take pieces of plywood and connect them at one point to provide stability in sliding, but allow them to hinge in order to allow them to form the smooth curves that we want to form. So what I'm going to do is I'm going to put together a few parts here on the table, and literally this design is so simple. I'm going to build this boat in front of you in real time, minus the 3 or 4 minutes it takes between steps for the 5-minute epoxy to harden up. All right, this is about all we need to do the initial build. Now, typically with the old stitch and glue technique, what would happen is you would take a couple of very identical panels that you've cut out of plywood, and you would drill a series of holes on one end and literally use wire to stitch together the end in order to provide that security from movement this way and movement this way, but allow hinging of the 2 panels away from each other to allow them to form the nice fair curves that we're going to produce. Nowadays, we have a better technique available, and that is to use very high strength fiberglass reinforced packing tape. This tape has an extraordinary strength. It's about 300 pounds of tear strength on this, and there's enough stickiness that if we give enough surface to the wood, we won't damage the wood when we take it off. It's faster to put on, and it will provide all the same advantages without having to do a bunch of drilling and then eventual removal of the wire. So the first thing to do is to take the 2 panels that we're going to be working with here and make sure that we've not only cut them very symmetrically, but we want to get the ends perfectly at the same point. We don't want to have any kind of misalignment, because that's going to determine how successfully we get a very even symmetrical curve. So when we've assumed we've gotten everything as about as perfect as we can, then we're going to put the tape on. And the tape, in this case, is overkill. We're not going to be producing anything like the amount of force that a full-size boat would produce, but this tape is sufficient that the model that we built that you'll see later was using the exact same tape, applied the same way, just more pieces of it. And roughly, I would say you really can't overdo the length. If you look it up, the shear strength on the glue is 30 or 40 kilograms per centimeter of length. So you're going to exceed the strength of the plywood after you get a couple of inches, or maybe 5 to 10 centimeters on each side. It's important when you put this on, not only do you assure that you're putting it on symmetrically and these things are lined up, but it's important to make sure that you squeeze the 2 parts together so you don't form a gap between the 2 panels as you're putting the tape on. And the reason I'm going to put on 3 pieces on each end is because I want to totally seal the front of the boat. There's a reason for that later. I'll explain to you. This really isn't necessary for additional strength. Once this has been taped, turn this around and we repeat the process on the stern of the boat. Okay, Now what we're going to do is we're going to set this thing laterally like this on top of another surface. You want to get this pretty flat, so if you're going to use sawhorses or something to put this on, you want to make sure that everything is pretty flat, because if you're doing the construction of any kind of a boat, if you have a nice, solid, predictable surface from which to work, everything tends to line up a lot easier than if you just sort of put this down on a garage floor that's bumpy or your surface isn't clean. Now what you're going to do is you're going to take advantage of the fact that when you spread the hull like this, you can see that you form something similar to the design that we're going to eventually build. And so in this particular design with a 9% thickness hull, we're going to move all the way back to about 40 to 45. I've got this little mark here at 43% of the way back. And we're going to put a spreader in here that's going to produce approximately 8%, not quite the maximum spread that we're going to want. And we're going to place this spreader, or otherwise called a bulkhead, at 2 marks that we've placed on here to make sure that we don't put this in crooked like this. And then once we have positioned this correctly, it's kind of a nice idea to get a square, something that you can use as a reference, to make sure that your surfaces are plumb with the sides, so we don't end up with a boat that tends to taper or taper. Once you've done that and you've lined this up in this position, then you're going to need to secure this particular bulkhead at the 43% point with a little bit of epoxy. Now ultimately what I'm doing is just a tack joint. We don't need to put this in to provide a great deal of rigidity or strength, because we're just tacking this into a position. Ultimately later on, when you're getting near the end of the construction, you can reinforce these joints that we're creating here with additional epoxy and what's called a fillet joint, where you take epoxy and you mix it with a thickener to provide additional strength to this zone. But this is just simply to keep everything from sliding around and repositioning itself during the initial construction. So it doesn't have to be neat and it doesn't have to be strong. Looks good. And now let's give it about 5 minutes to stiffen up. All right, it's been about 5 minutes and this glue it's gotten pretty solid. So we're going to go ahead and we're going to actually form the airfoil. And the way we're going to do this is we're going to take a dowel rod. In this case, this is a 9mm or 3/8 inch diameter dowel rod. In the full-scale boat, we ended up using a 5 centimeter or 2 inch diameter rod. And it's convenient to use this because it slips nicely between the surfaces. And so what we're going to do is we're going to put a little glue on this. We're going to place this into the bow of the boat. And then using a clamp, we're going to draw this in toward the bow. And you can see what happens when I just do this with my finger. This tends to have more curvature up front than this. This almost looks symmetrical from bow to stern. But if I put this dowel rod in here and I press it back, watch what happens to the width here and the width here. You see how the back end of the boat tends to narrow in over here. I'll put a little ruler up here just to make it a little bit easier to see what's happening. But you can see as I push this in what happens to the back end. It narrows in like that. And the front end tends to fatten up, which is exactly what we need for the airfoil. So what we're going to do is at this point here, which represents 25% of the way back, we're going to end up having to bring this out to approximately 11 centimeters. But the point is it will be at the 9% or the maximum thickness of the hull. So once this gets to that point, after compressing this, we've basically created the hull shape. This can get a little messy. I'm not using gloves, but I'll try to stay reasonably clean. I'll just put a little bit of this on here. This self-mixing epoxy from the big box stores, this is Loctite, tends to be very expensive per gram, but it's so convenient with the self-mixing that for these tacking operations, it's a good time saver. We're going to put this in here with the sticky sides toward the walls, and then we're going to snug it in about as far as I can with my fingers. And then we're going to take the clamp. I'm going to place this on here and start drawing it in. And you'll see what starts to happen here. This will be a little hard to see on the camera, but over time you're going to see that this is going to begin to broaden out and this is going to narrow in. Now in the big boat, what I ended up doing is I ended up drilling 3 holes in here, putting some threaded rods through the nose, and with nuts was able to clamp this in, because it's hard to get clamps that are, you know, this tall. But it works fine. Then you just cut the rods off when you're done. Stainless steel. Now see what's happening here? If you watch very carefully, I'll try not to shake the boat. You'll slowly see that it's getting narrower. But this is where the maximum load is also occurring at the ends. So if something's going to go pear-shaped, it's going to do it now. Now, where am I in terms of width? I'm getting there. I'm about 10 centimeters right now. Yeah, that's it. As you can tell, it's no longer that perfectly symmetrical shape, but we've drawn this in and we broaden this out. Now we're going to give this about 10 minutes to dry, and then once this is hard, we'll go ahead and put in the bulkheads that will reinforce this shape. And it's very important these are done just right. See you in just a bit. It's been about another 8-9 minutes, and now what I'm going to do is relieve this clamp, and hopefully if the epoxy sticks, the dowel will stay where it's supposed to. Looks good. Now I'm going to confirm that nothing slipped in the meantime. I have about 11 centimeters. It's perfect. And this is 25% of the way back from the bow. The maximum thickness is 9% the length of the boat. We have the form. Now, one of the things that you'll notice, obviously, is that this is extremely weak, and so it has to be reinforced. And the way we're going to do that is we're going to use bulkheads. What you do in this design, which is kind of a little different than you might do in most boats, is you usually design the boat, you do the drawings, and then you cut the wood to fit the drawings, and then you fit the pieces together. In this case, what we're going to do is we're going to place the bulkheads pretty close to equally spaced in order to provide reinforcement. But the important point here is we're going to provide reinforcement to maintain the shape of the hull that we have. We don't want to redefine it with these bulkheads. So for example, if I take this bulkhead right here, and it's designed to go at a point that I marked here at about the same distance from this primary bulkhead as the width of the boat. And each one of these individual pieces is going to be going into a space that has been measured and then cut. It's important that if you make a mistake and you cut the piece the wrong width so that it doesn't fit, don't think, oh, I'd better just force it in, because what's going to happen is you'll redefine the shape. So if your cut is not precise, don't worry about it. Just fit the bulkhead in to where it just kisses the surface, but does not distort the surface and change the shape of the boat. Again, these are to maintain the shape, not to define the shape, and that's critical. There's always a temptation to say, well, I marked it here, I better put it there. Don't do that. Now, the point with this is that once we've marked out these individual spaces, we're then going to fix these bulkheads at these locations with some additional epoxy. I've measured each one of these out to fit the location where they're supposed to go. And once I place them in the right order, then I'm going to adhere them with a little bit of epoxy, make sure that I line them up so that everything is plumb with the sides of the boat. And then once we've affixed these into the right position, then what we're going to do is we're going to talk about the completion of the boat with the top surfaces and reinforcements. Okay, now that this is hardened up, what we're going to have to do is reinforce the bow and the stern, because eventually we're going to want to take the tape off of here and we're going to run around this to a nice hydrodynamic shape. And because we probably won't want a feather edge back here, but we're going to want to cut this short so that we have a flat surface on which to mount hardware or like Pintles for, say, a rudder or an outboard engine. We're going to want to fill the space here and here with a thickened mixture of epoxy. I would recommend about a 50-50 mix by volume of wood flour and a very slow cure epoxy. We're going to be potting, in this case, putting a volume of epoxy in, and so you want a slow cure so that it doesn't build up so much internal heat that it damages the structure. Once that has hardened, I want to just also mention, actually to interrupt, is that you notice that these are solid bulkheads. You could, for the ultimate lightweight structure, actually place a hole in each one of these bulkheads that's about 50% of the outside dimension of the bulkhead to lower weight. We elected not to do that because what we're essentially accomplishing here is we're building individual flotation cells so that if we get damage, the whole boat won't sink and will Titanic down to the bottom of the ocean. So for a little additional weight, and it's less work, I just keep the bulkhead solid. At this point though, what we're going to have to do is we're going to have to decide how we're going to use the boat, and part of the final finishing of the structure is going to involve covering this up with the top deck. When we do that, we're no longer going to be able to see the location of the bulkheads, and so what you want to do is sort of cart before the horse. We've built the boat, now we want to draw the boat. Presumably you're building both hulls at the same time. That'll help to ensure that whatever kind of variations you make in your original intention, it's going to be similar between the hulls. But nevertheless, if it's not exactly according to the original design, having the location of all the bulkheads available to you after the fact will allow you to know where you can cut through for hatches and where you can put hardware. Before we go any further though, I think it's going to be important for us to decide how we're going to use the boat. And so that's what I'm going to show you next. Now let's assume that you're going to be putting fuel cells in this boat, or you're going to be putting storage batteries in the boat, or you want hatches that have a relatively strong inside so you can bang tools around inside of them. This is the opportunity for you to draw and mark a couple of extra pieces of plywood that you're going to use as doublers that you'll place into gaps in particular areas. You'll put this down on the drawing so that you'll know where they are, but you'll thicken up the floor, because to keep this light, the lower floor of this boat is quite thin, and we want to distribute load so that we don't damage them as a battery is bumping around inside. In addition to that, we also want to think about where we're going to be putting hardware. For example, if we're going to put a cleat and we're going to screw something down, we may not want to depend on the very thin material that's going to form the top of the boat. We may want to put additional material underneath to give some additional thickness so that screws have something to bite into. Again, you want to think about how you're going to be building the boat. That also brings up the whole idea of how we're going to actually connect the two hulls, and there's a variety of options for doing that. The simplest method would simply be to place a board across the two hulls, glue and screw it down, and you're done. But we lose the modularity there, and so we probably want something that's going to be demountable. Now, one option would be you could simply place a board across here, a doubler underneath, and a whole bunch of screws, and take them off and put them on each time that you deploy it. Another method that you could use, and it's a very neat method that was originally used by the Polynesians in their explorations across the Pacific for thousands of years. And James Warren, in his Tiki designs, which are trans-Pacific sailing craft, use this same kind of design, and it's pretty clever. What they do is they take an element like this, a wood channel that has been fabricated with a trough inside of it. You could do this out of fiberglass or build this up from wood. And you place it on the surface of the boat so it provides a support for a cross member like this. And then what you do is, using either a thickened piece of material inside to give it a little bit more strength, or you could actually fabricate something where you bolt clips on here, but a rod through this hole actually acts as a nice support. And then what you do is you take a crossbeam. Now this could be a piece of metal pipe, it could be a piece of fiberglass, or a wooden log, piece of bamboo, and you place it into the channel, and then what you're going to do is you're actually going to lash it down. And the way to do that is you're going to place a small piece of string here, and we'll see if I can do this opposite. I'm left-handed, and we'll see if I can manage to do this anyway for the camera. But you're going to want to wrap a couple of wraps around here of the lashing. And then once you've done that, what you're going to do to give this some strength and some tightness is you'll pass the cord around here a few times to cause the entire circle to become tight here. And when you do that, it creates a very strong lashing, and you'll do that on each side of the hull. The advantage with this kind of design when you finish with this is that obviously you can take it off and you can put it on. It's extremely strong because it distributes the load across a large area of the boat, and it also retains a little bit of give. And so what the hulls do, and that's what made these boats so seaworthy, is that the boats almost act like a vehicle with independent suspension. As one hull rides over a wave, the passengers in the middle don't feel all of the disturbances, and the boat can sort of flow with the water and the irregularities in the surface. It makes it tough, it makes it more comfortable. It's been around for a long time, and it's extremely inexpensive. One disadvantage of this technique, as well as putting a board across here, is what's called freeboard. That's the distance between the deck that you eventually put on the top of the boat and the level of the water when it's immersed and loaded. And in this kind of an application, unless you have a very tall hull, you're going to have a rather low freeboard, and therefore you're more likely to get water on your feet and get spray depending on the weather. And so what we elected to do is to use a technique where we actually created a bridge using pipes. Effectively, what we did for the main size boat is we used some Schedule 40 2.5-inch OD aluminum pipe. It comes up to 7-meter, 24-foot lengths. And we had them professionally bent into curves, so that what happened was we were able to support the boat or the deck arbitrarily high above the hulls, so that we could keep the hulls relatively small and light, but we can get whatever freeboard we want. It's inexpensive, it's extremely light, it's deployable, we can take it off and put it on. And in order to fabricate the support that we're going to use for this, I'll show you the trick that we used, and it's kind of neat. Inside of the hull, we anticipated that we were going to put it in this section here, so we put a doubler here that's going to produce a little bit more load capability of the thin material up here. And then what we did is we took a bunch of pieces of plywood, glued them together into a thicker component, and then drilled part way through them, so that when we insert this in here, we have both a reinforcement for the floor as also including a receiver for a larger diameter tube that the support can fit through. So when we put the top on this boat like this, and we insert the receiver into the cup down there, we have an oversized hole to allow us a little bit of misalignment and freedom when we put this thing together, so it's not too rigid. And then we just fabricated a reinforcement ring that goes on the top here, maintains a perfect position so this is plumb, and also distributes the load with some screw holes around here to provide a very strong structure. This not only ties the two surfaces together and produces, again, a very strong piece of material, this prevents hogging that this thing would eventually do if it was constantly banging against the side when this thing is on the water. And also, because this is glued at the bottom here and glued around here, this is waterproof. So if water pours in here, it doesn't fill the chamber inside of here. So that's the method that we ended up using, and I think it's probably the best because it is very flexible. If you look over here in our test model, we built a little cheaper version of this to allow us to play around with dimensions. And you can see that it obviously provides a lot of strength this way, and it prevents a lot of strength from bending like this. But it does not provide any resistance from scissoring, because obviously these can rotate. So finally, on the final boat, and as you can see in this model, what we did is we simply mounted some cables with some clips and these screws that allow us to pull in the cable and essentially tighten up the hull in order to provide a structurally rigid structure to whatever level of amount of flexibility we want. In addition, if we didn't fabricate this thing perfectly, by adjusting the tightness on these two, we can kind of take out any kind of errors we have in the structure, so we get a nice square support for our deck. This is excellent. I'd highly recommend doing this because it worked out very well. Now, this model that we tested on the lake is so efficient, it was difficult to test it. We found that when we were tow testing this for drag and alignment and buoyancy points, we found that it was so hydrodynamic that every time the little tow cable would get a little tense behind the towboat, the boat would spring forward and ram into the back of the boat. It just wouldn't run out of speed before it caught up to the boat. It was incredible. In addition, it tracks very well. Even if we pull this at about a 45-degree angle to the angle that it's aiming, it still continues to track straight forward. So for sailing applications, we don't need any additional keel or anything else to keep this thing aligned. That has to do with the fact that these are airfoils, they're hydrofoils, and they want to go straight. Once you've fabricated this, you'll notice a couple things. We don't use up the entire length, and that has to do with the fact that, unlike Grandpa's pontoon boat, these boats do not have a lot of buoyancy at their ends, because obviously we've gotten a taper here. And so even though this is extremely stable laterally, it is not very stable longitudinally. So one of the things that we decided to do when we built the final boat is that once this has been glued down, the inside sealed, the top has been glued down, and everything is ready to be sort of fabricated to the final shape, we only trimmed the top to form the shape of the hull. The bottom we left whole. We trimmed it and rounded it a little bit, but basically the bottom in the back was left intact to act as a fin, so that what happens is when the boat wants to do this tip, you know, when a wave hits it and it wants to go up like this, by having the fin at the other end, it changes the angle of attack on the fin, and so instead of the boat going like this with waves, it goes like this with waves, and it becomes much more stable. And it's easy to do because it's inherently part of the structure. We don't have to add anything. It actually saves work, doesn't cost us any money, and was a good modification to the simple hulls that we used on the original test model. The other thing you'll notice too is because the buoyancy still is somewhat limited at the ends, the deck is limited somewhat to the center portion of the hull. This helps to maintain balance even if people move around, because they don't have the ability to move all the way to the bow and the stern. Another thing to keep in mind too is that the balance point of your hull is going to depend on the shape of your hull. For a reference on our hull, it turns out that the center of buoyancy is approximately 40% of the way back from the bow. As this becomes fatter and this becomes narrower, it's obviously going to move forward, and you'd have to experiment with each one of the shapes, or you could do a measurement of the area of the hull if you're willing to go to the Airfoil Tools site and look at their calculators. But for our purposes, it's about 40% of the way back, and so we centered our deck about that point. So when people move around, this thing shouldn't tip that much from a flat orientation in the water when it's floating. Next thing is the deck. We want this thing deployable, and we don't want to produce a permanent deck, and we don't want anything too big that you couldn't put it easily in the back of a truck or a trailer. And so what we did is we fabricated these planks that have a longer upper edge than the bottom, so that what can be done is these simply can be dropped between the bars, the horizontals, to form a deck that is lightweight in its individual components, but is also arbitrarily wide and arbitrarily long depending on how this ends up being built. So once you've built all this, you then cut these to fit. Now, one of the limitations here is that these individual boards, because they are individual, are not working together. They're just sort of laying next to each other. And so if you got a big heavy guy bouncing around on the boat, unless you build these things very strong, they're going to tend to do this. So in the final model, when we built the box structure, what we ended up doing is allowing some of the verticals to be proud and some of the verticals to be recessed, so that when the boat is put together and these things are hung on the front of the bars, they key together like this. They become a single entity. And then when we put tie rods between here and tie rods between here, we form a very rigid deck that's nice to walk around on without having to overbuild the structure. That's about it for the design in here. And so what I want to do now is I want to go outside, and what we're going to do is we're going to cover some of the differences between this and the full scale. So let's go outside and take a look at the real boat. All right, this is the real thing. This is 4 times the scale of the model that we showed you inside. So its overall length is 16 feet or 5 meters. Its overall beam is 3 meters or 10 feet. Each of the hulls is half a meter high or 21 inches. They're fabricated from 1/4 inch Okumi plywood for the stressed component and 3/8 inch or 9 millimeter Sapelli, which is a stiffer, a little more expensive plywood for the deck and the floor. The surfaces were sanded, they were glassed, and then each of them is covered with 2 coats of a 2-part polyurethane paint from Interlux called Perfection paint. It's a very high gloss and very hard marine paint, and the overall structure is extremely strong. It's probably overbuilt. The weight of the boat, empty as it is right now, is about 110 kilograms or about 240 pounds, so it's not that heavy. As you can see, these are the aluminum spreaders or load spreaders that we placed at the penetration point for the Schedule 40 pipes that enter the hull into those receiving tubes that I showed you inside. In addition to providing a load spreading application or a load spreading service, what they also do is they provide a hard point where we have placed some eyelets, some little eye rings, and then we take clips and we place them through holes in those pipes and can retain the pins down, so this prevents the pipe from coming out depending on what kind of conditions you're sailing through. In addition, you can see here the cross cables that we put in order to resist the scissoring action of the structure. They have quick disconnect pins over here and then turnbuckles that allow us to tighten them up and adjust them when we're on site. Because of the fact that we designed this and we put the drawings down before we closed everything up, we knew where we could put penetrations through into the deck, and so we put a hatch, waterproof hatch, that allows us to store items. So we can put tools and extra line, supplies, and foul weather gear. Now, if you look here, you'll see a cross member which wasn't part of the design, and I'll explain what this is used for, but it's simply a square box channel of aluminum that's retained on some hard points that has applications. We'll get into that in just a little bit. But this isn't structurally necessary, it's just added for future purposes. The poles are identical here, and they attach or support the deck, which rides between the 2 poles here and is secured by these 7mm or 5/16 inch diameter stainless steel tie rods that extend all the way through at these 2 points laterally. And then when we go around to the front, you'll see that I have 2 similar tie rods that run longitudinally. And these things apply force to lock the deck into a single monolithic structure, which makes the whole boat a lot stiffer. Okay, so as you can see here, we have a cleat that we mounted on the front in order to be able to support line. We added a couple of extra layers of plywood under the deck here to give the screws more purchase in order to give this some strength. And it's something you might also want to think about if you're going to be using this boat as in a sailing application, having some additional plywood up here to support a forestay or other hardware that we're going to want to screw down to the deck. Think ahead. Now, something else I didn't talk about in the model inside is that in order to retain the deck onto the pipes and keep it from riding up, we have an aluminum C-channel that is squeezing the deck down onto the pipe and is pushed in and held secure by the 2 longitudinal tie rods that we have here on nuts that allow us to squeeze its mate against the pole from the other side, so we can essentially force the deck into one unit. And then if you can see these little rings over here and over here where I have these temporary knobs, this is simply to allow us to extract the C-channel from this structure, because when the wood swells up and this gets really tight, it can be difficult to remove. So these are just a convenience factor. Now I think it's time that we talk about propulsion. Now, originally we were going to use an outboard engine to power this, and one of the considerations you have when you've got a boat with this type of design is that it has a very high freeboard. It's almost a meter above the water. And so it would be rather difficult to mount a typical outboard on top of the deck and have the shaft still in the water. There's another problem that you have with this type of a boat with a rather limited deck, and that is that a typical tiller steering type of outboard produces its ability to turn because it's creating a force or a lateral force at the rear of the boat, so that allows you to maneuver. But when the force is being applied near the center of buoyancy, what happens is if you try to use a tiller in order to steer the boat, what you're really doing is producing a lateral force, kind of a midships, and the whole thing is wanting to just slide sideways as opposed to turn. So it wouldn't really be very practical to use a typical outboard, and because of the fact that we wanted to experiment with different types of drive systems, what we did is we went ahead and got what's called a mud motor, or a Thai longtail swamp motor. What's neat about these things is they're used all over Southeast Asia, they're used in South America. They use inexpensive, typical 4-stroke, 2-stroke outboard engines, internal combustion engines, and then simply mount a very, very long shaft onto the end of the engine to allow you to produce fairly lateral force by just slightly inclining the drive relative to the surface of the water, so that eventually the propeller is in the water, even though this is up on a transom. The reason we decided to use this kind of a motor is because as long as we knew that we couldn't really steer with the motor itself, and because this is a lot cheaper per horsepower than a regular outboard, we thought we'd put this thing on that cross member that I was talking to you about before that runs underneath the deck, and just hinge it to allow it to drive the boat with a propeller located near the stern of the boat. And then what we were going to do is to use a couple of rudders similar to what you would do on a sailboat. And you would put these down on some pintles, put them at the rear of the boat, and then use an actuator to be able to steer the boat remotely. And we elected to use electrical actuators similar to trim tab actuators that would allow us to drop the rudder onto the pintles, clip this onto the end of the rudder, and then just plug a 12-volt line into this to run it up to a joystick in order to be able to steer the boat. By producing the force at the stern of the boat, what that allows us to do is produce a much larger moment arm and give us a lot more maneuverability. However, we built this boat as a test bed for a variety of different types of propulsion systems. Both gasoline, we were going to be using hybrid, we might use a sail, kite sail, mast sail. We might look at steam engines, a Stirling engine. And so with that in mind, we thought maybe the most interesting way to start would be the electric drive. Electric outboard engines have become very popular. However, they are very, very expensive. And for this scale boat, I would say Torpedo is probably the most competitive model out there. But still, you're talking a couple of grand per motor. And so what we decided to do instead is to use trolling motors. Now, from my experience, the very best trolling motor out there is made by Minn Kota. But it's also still pretty expensive. And so what we decided to do is to get what I think is probably the best of the Chinese clones, which is the Newport trolling motor. It's a 24-volt, 86-pound static thrust motor on each side. And the motor has a fiberglass shaft that would normally be attached to the controller and would obviously be very difficult for you to operate from this distance. So what I did is I cut through carefully the fiberglass shaft and took a segment out so that I would have some bare wire to work with, and connected the extended wires, there are 4 of them, into a very long, much heavier gauge cable that then carries the control and the power all the way forward to the front of the boat where you saw the controlling end of this outboard. Then place this on a clamp that allows me to adjust this in height as well as rotation, clamp this down, and then placed it with a little hinge pin here that allows us to extract the motor from the boat when we're done using this or when we're getting ready to put this on the water. In order to keep the motor in line, what I've done is I fabricated a little tapered aluminum channel here that acts as a support as well as a fairing to provide much better hydrodynamic flow around here than the nasty flow you get around a circular structure inside of a water flow. And then at the bottom, as you can see, we have a little pin that's been placed in this fairing, and there is some sacrificial aluminum wire that we wrapped around the pin. The purpose of this is that this wire is strong enough to resist the full reverse flow of the force of the motor. But if we were to strike an item or a log or something on the bottom of the water, this wire will snap and this thing can hinge up so that we don't damage the motor and we don't damage the boat. It's also easy to remove and put this on. We can just wrap that on in 30 seconds when we're on site. Now, as you notice, this doesn't look like you'd expect a normal trolling motor to look. Problem with trolling motors is that they're designed to keep very, very heavy boats from moving or move them at a very slow speed, trolling motors. And so in order to be able to move very quickly, these things would have to rotate faster than the design of the motor. And in order to be able to move faster than about 5 or 6 knots, you can't use one of these propellers, because basically at that speed, the propeller is basically just keeping up with the speed of the boat. No matter how light the boat, it won't move any faster because you're just screwing through the water with the boat. And it's a problem that some kayakers have found, that when they take these rather powerful motors and lightweight batteries, even a very light kayak begins to top out at around 5 to 6 knots because the propeller just simply can't keep up with a higher speed. If you go online and try to find a coarser pitch trolling motor propeller, you won't find them. To begin with, they're very poorly specified. Generally, people say weedless or they say high performance, but they really don't give you a pitch. Typically, the pitch is about 2 to 3 inches of advance per rotation, or you can figure out the metric equivalent. And even though there are slight differences in performance, and people swear by one kind of prop or another, but you really can't change the overall ability to move fast through the water by staying with a trolling motor propeller. So what we elected to do, based on some success people have had with kayaks, is go to an RC airplane propeller. This is a master screw, 3-bladed, pusher propeller, 15-inch diameter, 7-inch pitch. That's how it's specified. It's in imperial, so you have to do the conversion. It only costs about $16. Because it's pusher, it allows it to rotate in the correct direction and produce thrust. If you look into this, you'll find that all gas propellers, which would have been the other alternative, need to go in the opposite direction. And so that's a nice thing about these. They come in pusher and tractor design. In addition, they have an extremely efficient asymmetrical airfoil, which makes them very efficient in the water. And if you decided that the only thing you want to take from this project is this idea, and no matter how small or large your trolling motor, I would get that particular propeller. It's a glass fiber reinforced nylon. It's waterproof and it's very tough. And if your trolling motor isn't capable of driving such a large propeller, simply trim the diameter down so that you maintain the thick web, and the 3 blades divide the load, rather than getting some lightweight park flyer propeller that's going to bend and twist under the load of driving the boat. This brings up the issue of power. These motors are 24 volts, and each one will draw about 1,300 watts. And so in order to be able to move this boat any kind of reasonable distance, you're going to need 2 pretty good size deep cycle batteries per motor. 4 batteries of that size are going to weigh as much as the entire boat. And so, thanks to Elon Musk, we decided to do something a little different. So here we have a single module from a Tesla S. There are 16 of these in the car, and each one of these modules contains 444 of the 18650 Panasonic cells, set up an array of 6S. 6S meaning it's 24 volts, which is convenient for our motors. In addition to that, it has the ability to be charged by a typical standard RC charger that can charge 6S. The system comes with a battery management system that normally plugs into the computer system for a Tesla. You can tear that off and simply pigtail the 7 leads necessary to be able to remote that, and therefore you can use a standard battery monitor system that is used for RC applications, allows you to measure the voltage of the battery when we're operating it. In addition, this can then be unplugged and put into a typical RC battery charger in order to be able to balance charge the battery. Each one of the cells in here has been wired into the apparatus, into the system, with very tiny lead wires that actually act as simultaneously as fuses. So if any one of these individual cells were to go haywire, blow out, it would not destroy the entire battery. It would simply blow out its tiny little fuse, and you would lose a tiny bit of the capacity of the battery, but the battery itself would be completely usable. In addition, at this end of the battery, we had to blow out and clean out and seal up the cooling tubes that run through here that in a normal Tesla would allow this battery to be cooled and warm to keep within a normal temperature range, or an optimal temperature range. For the very gentle use that we're going to be putting this battery to, we're not concerned about heating during charging or discharging. This battery can produce up to 1,500 amps continuously. At most, we would draw 100 out of it. As you can see, at this end of the battery, we have these very heavy 6-gauge cables that are then attached to the 2 leads that come out, one for each of the motors, through waterproof fittings, and the entire thing has been placed in a waterproof cell so that we can see what's going on in here, but water can't get inside. The top surface has been gasketed down, held down. This entire structure is not light, but it is remarkably powerful. This single battery here costs about $1,000 on eBay, And that might sound high, but 4 good quality deep cycle lead acid batteries are going to probably cost you about $600. In addition, the capacity of this single module is 5.3 kilowatt hours. 4 lead acid batteries would not even be able to produce that much power. It would take 6 lead acid batteries to be able to produce the same amount of total usable capacity as this one module, and this module weighs less than a single battery. It also has more cycle life, and because of its compact nature, it allows us to mount this thing underneath the deck, as I'll show you in just a bit. But it makes it also easier for us to get this in and out rather than having to dump this into the hulls. So let me show you how this fits together, and we'll run this thing up. So forward, reverse, and left and right. And so because we can control the thrust on these motors, forward and back, left and right, we don't have to articulate these motors in order to turn, which keeps the operation a lot simpler. Now, anybody familiar with boat design might realize that the speed of this boat, which is a displacement boat, typically is limited by a property called hull speed. And it has to do with the density of water and gravity. And effectively, it is the speed limit beyond which the hull no longer efficiently travels through the water, because the water is simply unable to fill the void left behind the boat, and it starts to produce a bow wave that creates a great deal of acceleration because the water simply doesn't have time to move around the hull in a steady laminar flow. That speed is often designated by an equation which is in knots, 1.34 times the square root of the waterline length in feet, or 2.4 times the square root of the waterline in meters. This is a 16-foot hull. Square root of 16 is 4. 1.34 times 4 is about 5.4 knots. So you might be wondering, why do we want a propeller that allows a boat like this to be able to travel at 3 or 4 times the hull speed? And I'm going to answer that question in just a second. I'd like to make a little appeal. A short time ago, we decided to take this channel from a few hundred subscribers and several videos for laser enthusiasts to cover a much broader range of technologies and the variety of projects that we have been involved with over the years. And in less than 2 years, we've expanded to nearly 300,000 subscribers. Because of that success, and because it's so much fun doing these projects, and even more fun, it's a blast to share what we've been doing with all of you. We've decided to take the next step and go from a part-time weekend and evening activity to a full-time project. And that kind of commitment is going to mean that we're going to get better video skills involved, we're going to get better video equipment, and more importantly, we're going to expand the content. We're going to cover big projects like this, as well as more frequent videos that cover smaller, useful topics, like how do you glass a hull, or how do you steam bend oak, how do you do resin infusion, how do you vacuum bag, when do you use Kevlar, when do you use graphite. Even if you don't want to build one of these big projects, you might find some of those technical videos very useful and kind of interesting. And to justify that kind of commitment on our part, we need your help. And I don't mean direct financial help. If you like what we're doing here, give us a thumbs up. And if you spend a few more seconds, if you can give us a comment, even if it's something as simple as, hey, I like the video, or I hope you can swim, that triggers the YouTube algorithms to promote us or to place us on the recommended list, which expands our exposure to a much wider audience and helps us to grow. Even more importantly, if you share what we're doing, either with other content creators, on forums that you visit, on Facebook and Instagram, on Gab, on Reddit, family picnics, PTA meetings, even graffiti at your favorite train station. Just kidding, you don't want to be defacing any property. But that kind of support, that kind of exposure will helpfully expand this channel to the point that we can target several million subscribers. In return, we will continue to try to provide better content and more frequent content. And before I leave you, I'd like to answer the question that I posed before. Why do we have high-speed propellers on a boat that shouldn't be able to go more than 3 or 4, maybe 5 knots? This is a hydrofoil. You see why you might just want to subscribe? Thanks a lot for watching. You have a wonderful afternoon, and we'll see you soon.